Now let's look at the sum and difference rule. So what happens if we're adding or subtracting two functions and then we want to take the derivative? So here I want to add f and g and then take the derivative. Well, can I do it in a different order? Yes. I can actually take the derivative of f, take the derivative of g, and then add them. Similarly, if I want to do the difference, f of x minus g of x, and then take the derivative, I can instead take the derivative of f, take the derivative of g, and subtract. Okay? And so let's see basically these past few rules together. Okay? So if I'm looking to do this derivative here of this little polynomial, what I'm saying is, more formally, is that we have these three terms being added. So what I could do is do them individually. Alright, so when I get to take the derivative of 3x cubed, I can use this idea before. The 3 is going to come down, multiply that 3, be a 9. Then I have x to the, take 1 away from the 3, squared. 9x squared. And then I can move to the next one. So now I'm going to take the derivative of the x squared. That's just 2 comes down, x to the 2 minus 1 is 1. I don't need to put that. Okay? Now in this last one, I have this constant multiple 2, which can stay there. And then the derivative of x, we already saw, was 1 because it's x to the 1 and 1 x to the 0 is 1. So I actually only get 2. So what we're going to see is that when you ever have a constant times x, the derivative just ends up being that constant. Alright, so let's look at b here. The derivative of negative x to the fourth plus 2. Alright, the derivative of negative x to the fourth, so I have a minus, that's a constant multiple, really is a minus 1. Then the 4 comes down, so minus 4, x to the 4 minus 1 is 3. Okay, and then I have an addition, so then I can do the one separately. And now the derivative of 2, well, 2 is a constant, its derivative is 0, so I really have negative 4x cubed. So this is a very nice fact that we can do sums and differences piece by piece. That makes it a lot easier. So if I ever see a bunch of functions added or subtracted, I can just do them individually and then add or subtract them as needed afterwards. And that's something we're going to do all the time. Okay. So now there are some functions that we're going to have to just basically learn their derivatives. We could, again, prove this using the limit definition, but we don't want to do that and do that every time because we'll get bogged down in the details of this. So there's a lot of functions that we basically just need to know by memory or by being ingrained in your head after having looked at it so much, what their derivative is. So the first two that we're seeing here are sine and cosine. Okay, so the derivative of sine x is cosine x. And the derivative of cosine x is minus sine x. Okay, and that's how it works out from the limit definition. And so instead of trying to prove that every time, we're going to remember those. Okay, later on we'll bring in the other trig functions, but not quite just yet. All right, another very important and interesting one is the exponential. Okay, so the derivative of e to the x is a hugely important idea in calculus because e to the x is the function whose derivative is itself. And that's hugely important. That means that at any place on the curve e to the x, the rate at which it's changing is equal to its value. That's unique to the exponential function, making it very special. Okay, so that's the natural base e. In general, if we just had any other base, a to the x, the derivative of a to the x is a to the x, so it does give itself back, But then there's something that I like to call a correction factor. So I'm thinking it as a correction factor because it's not base e. So you get multiplied by ln of a, okay, the base. So that's the difference there. All right, let's see some examples here. So the derivative of 4x plus 3 sine x. Okay, they're being added, so I can do them individually. The derivative of 4x, well, again, we said that anything times x, any constant times x, will just give you the constant back, so that's 4. Plus, now I have a multiple 3, constant multiple 3, that stays around. And then I do the derivative of sine x, which we just learned was cosine x. Done. Okay, how about b here? These 1/2 e to the x is being added to cosine x, so I can do them separately. All right, 1/2 e to the x. I have a constant multiple. Realize I'm saying that it's constant multiple because that's a big difference between a constant being on its own and a constant multiple. A constant being added or subtracted on its own would have a derivative of 0. But if it's a constant multiple of another function, then that multiple stays. So 1/2, and then the derivative of e to the x is itself e to the x. Okay, so then I'd have plus, and I take the derivative of cosine x. All right, the derivative of cosine x, as we learned before, is minus sine x. So I'm going to change that plus to a minus sine x. So 1/2 e to the x minus sine x. All right, so now f of x is 2 sine x minus 6 cosine x plus 17 e to the x. So now we're doing it in just slightly different form. We're doing it in the prime notation. So if this is the function here, then the derivative would be represented by, okay, go here, 2 sine x. 2 stays around as a constant multiple. Sine x becomes cosine x on the derivative. Then I have minus 6 as a constant multiple. Derivative of cosine x is minus sine x. So this becomes a positive sine x plus 17 e to the x. 17 constant multiple stays. E to the x, its derivative is e to the x. Okay. Now let's take a look at d here. The derivative of 2 to the x. Okay. That's the more general exponential rule that I was talking about up there. So what I would say is, it's like e to the x in that it starts by returning itself, but because it's not base e, I need that correction factor of ln 2. All right. This is a good place to make a very important point. Okay, the difference between the derivative of x squared and the derivative of 2 to the x. Okay, and this is why it's important to notice the difference in types of functions. This is a power here. It's a power of x. X is in the base and the number's in the exponent. This is an exponential. The number is in the base and the x is in the exponent. These are very different functions and have very different rules for taking the derivative. We've seen that this would be that power rule, so 2x to the 1, or just 2x. And now we've just seen that this would be 2 to the x ln 2. Okay, so we have to understand, especially if we're going to be using these rules, that what type of function it is matters a lot. And so we have to be applying the correct rule for that type.